Okay. Welcome to our YouthSTEM Science Fair workshop. My name is Angela Jean, and I'm the president and founder of YouthSTEM. YouthSTEM is a national nonprofit organization that aims to help students get involved in STEM. And so our speakers today have a lot of experience in research and science fairs, as they are all Broadcom Masters or ISEF finalists. If you have any questions, please put them in the chat and we'll answer them after all the presentations. So we'll begin with our first speaker, which is Rika.
Okay, let me share my screen. Okay, can you guys see my screen?
Yeah.
Okay, perfect. Hi everyone, I'm Rika and I'm the Secretary of YouthSTEM. And just a bit of background, I was a top 30 Broadcom Masters finalist in 2021, and I was the recipient of the Robert Wood Johnson Foundation Award for Health Advancement. And since then, I've done a lot of research like on my own with professors and had some publications, some research awards, and I've also continued to do science fair at my county level. So today I'm going to be talking about how you present your research because you want to make sure that you can effectively convey what your message is and what the goal of your research is to someone who's listening, whether it just be like a general audience or a judge. So science communication really is like an art, and then it is something that you can learn and that you can become better at with practice. Okay, so first of all, why would you want to present your research in the first place? I mean, in most scenarios, you'd have slides or you'd have a poster. So what really gives you the need to have to communicate this and talk? Well, research isn't for yourself. It's for the society and the people around you because the science community is trying to learn from what you have studied and what you have discovered. So you want to present your research to essentially just share your findings. And you also want to learn from others because people can actually give you useful comments like in science fairs or at any conferences. People have the opportunity to discuss your work and they can give you really important comments that you can implement into your own research or things that you can use when carrying out future research projects. So you want to present your research to ensure basically advance society because you're discovering new things that haven't been done before, and being able to present these and being able to actually voice what you're finding out is something that other scientists can learn from and something that can be used to solve modern day problems, etc. And also just to have fun. It's a fun experience to share something exciting that you found to other people as well, and to kind of receive that excitement back from your audience. So now when you're presenting your research, you do want to keep some things in mind on how to present, and you want to be able to figure out what you can say to most efficiently or effectively convey your message. So what you want to do is there are five main principles. So you want to decide your main message and tailor it to your audience. So what I mean by this is you want to figure out what the main idea of your research point is. Like you want to think of like an elevator pitch, kind of like a 1 to 2 minute elevator pitch. What is it that you're trying to do with your research? What problem is it solving? What are you getting from your research? And by tailoring it to your audience, I mean, if you're presenting to like a bunch of second graders versus to college students, professors, obviously the way you're going to talk to them and the way you're going to convey your message is going to be different. So if you're talking to like people who are younger or people you're trying to teach them, right? If you're trying to teach people who are younger than you or people who might not have as much experience in scientific research, you want to make sure that the way you're speaking to them and the way you're voicing things, you want to make sure that it's in digestible terms. So you want to make sure that they can actually understand what you're saying. And this means like if you're using technical terms, you want to make sure you completely thoroughly explain them. This is like actually in any scenario, you should be able to completely explain through what you're saying, like your terms and everything, because you can't make assumptions that the listener already is familiar with what you're talking about. So you want to make sure that you can actually explain everything thoroughly. But again, if you're talking to professors or people who have more experience, then you should mention more of those details and go more into depth into what you're doing. So you want to explain it, like similarly, you want to explain it without jargon and you want to explicitly spell out the research question. So you don't want there to be any ambiguity on what you're trying to do and what problem you're trying to solve because that's essentially the main, like when you're doing presenting at a science fair, for example. That's a competition. So the judges are actually trying to find who knows their project the best and who has the most relevant idea. They're not gonna focus too much on the fluff and the extra details. They want to know what your research question is, and they want to know exactly what are you doing to solve that. And then from there, they think about the relevancy and other topics, but the main thing comes from your research question. And then obviously following that, you want to tell your audience about the main findings because it is important to know what you contributed, and it is important like that they want to know what you found and how that can make a difference. So at a science fair, the main points of your presentation would be the research question, like what are you trying to solve? Your procedure in the middle, you want to explain what you did to solve that problem, and you want to explain what you found from there because that essentially is the main part of your project. And then, of course, you want to focus on the practical application of your research. So what that means is you want to actually talk about how your research can be applied in real life scenarios, because if it's something that's completely like unreasonable or impractical, it's typically not really like well received by people who are like judges, etc. These judges want to find out if your research can actually be applied in the real world. They want to see if this can actually be used to solve a currently existing problem, not just something that would be impossible, take tons of money, not something like that, because again, we're trying to solve a problem here. So you want to focus on the practical application of your research and how it's going to be used to solve the problem. So just kind of going more into the 5 principles, I kind of talked about it generally, but so first of all, let's talk about the main message and really go into what we're trying to convey here. So I gave you kind of a general summary of each of the principles. So first, for the main message, it's kind of like a business model in a way. The way companies try to market their products to other people, how they do that is kind of how you're trying to sell your project to your audience. So first, you want to understand who your audience is, and you want to actually create an emotional connection with them. So you want to actually have some kind of story behind why you're doing what you're doing so that they can empathize with you and they can understand what the project's about. You want to mention your direct points, and you also want different strategies depending on who you're talking to. And you need to have a practice message. You have to go through a lot of different kinds of elevator pitches. Like you can write down a bunch of different summaries, and then in the end, figure out which one's the best, which one's most effectively gets your point across. So now explaining it without jargon, again, you want to use simple language. Again, you should have your technical terms, but as I mentioned earlier, if you have your technical terms, you want to make sure to explain them thoroughly and clearly so that the audience can understand what they're talking about. Again, don't make any assumptions. Just go in and present assuming that they don't know anything. And don't use language that is specific for a community. So like be formal, be plain with your English. Don't change the way you're talking based on who you're talking to. Just the level of explanation should be something that you should consider. And then next, you want to make sure you explicitly spell out your research. So you want to specifically mention what problem you're trying to solve, like if it's been done in past research or not. What are you trying to change? What are you trying to do essentially? Like what is the motivation behind what you're doing? And you also want a specific question. Like you want to make sure you're having a clear question that's not too generalized on what exactly you're trying to do. And honestly, the more specific, the better, because you want to make sure that it's a very clear line of what you're trying to do. Again, if you have something too general, then it typically is not received very well in science fairs because they don't want something really broad, because something that's really broad is less applicable. They want something that's solving a very specific problem. And then also just be aware of what kind of language you're using. Like you don't want to use language that shows subjectivity. Like the words like better is a value judgment. So that means that not everyone is going to think one thing is better than another. It's subjective. So you want to avoid the subjectivity and be more practical and objective. And then you want to tell your audience the main findings. So this kind of goes back to principle 1. So you want to, of course, understand your audience, and again, your findings are going to stay the same no matter who you're talking to, but when you actually present them, you want to tailor your findings in a way that your audience will understand. So again, if it's in very super scientific terms, you want to make sure to not dumb it down essentially, but like be able to explain it in simpler terms to your audience. And then visual aids like graphs and things like that are really important for breaking monotony. So you want clear visuals, and having an actual graph with like lines is better than a table, because a table is, again, they're just reading a list of numbers. A graph helps them visualize it better, and this aspect is probably going to be on your poster. And you always want to focus on the big picture of your research. So if you have a significant result, you don't want to just say, oh, this is what I got and this is really important. Why is it important and why should people care about that? You want to explain why something you found is relevant to our society today, because that's what the judges at science fairs are looking for. And the last thing is try to tell a story. So remember that the judges, your audience, or whoever you're talking to, they're human, and stories interest them more than just a lecture. So you don't want what you're saying to them to be a lecture. You want to actually keep them engaged throughout the entirety of your presentation, because at least in the case for science fair judges, these people have to see like 20, 30 people, like a lot. They have to go through a lot of presentations, and they have to listen to so many people explain their research. So you want to make sure you stand out, and to stand out and be memorable, you want to make sure that they actually are captivated by your presentation, and that you want to make sure that they actually understand and they're interested, because really your project is only half of it, but the way you present your project is the other half, and that can actually determine whether or not you make it to the next round or not. Okay. And the last one is practical application. So why does your research matter for society or for humanity in general? So you should always have a message at the end for society, because the whole purpose of scientific research is to solve problems to help humanity. So you want to make sure that it's clear how your results can be used to make society better, because you want to have a very general, like a very broad application from your research, but your research should be itself should be solving a specific problem. So you want to give some policy implications. How will this impact people's lives in the future? How far of a reach does your project go? And obviously, a huge part of presenting your research comes from designing your poster. So there will be a workshop, I think, later on about how you can design a poster. So take the information you learn from designing your poster and apply that to your presentation as well, because your poster is going to be your aid when you're presenting your research. So you want to make sure that you can effectively use your poster to show your audience different aspects of your research and be able to more effectively communicate. And most importantly, have fun and enjoy talking about your research to your audience. Yeah, I hope that was helpful, and thank you so much. If you have any questions, then feel free to ask. Okay, thank you.
Hi, I think I will be in charge of the next section, so I will just screen share. Please let me know if there's any issue with hearing me or seeing my screen, but I think it should be good. Um, so yeah, all right, I will get started. So hello everyone, my name is Snigdha Mohanraj. I am a junior from Connecticut. I'm the vice president of activities and one of the co-founders for YouthSTEM. For me, I've been doing science research, science fair since I believe sixth grade, seventh grade. Um, I specifically been working a lot with water contamination, and similar to Rika, I did Broadcom Masters and was one of the top 30 finalists in the country. After that, I did the 3M Young Scientist Challenge in eighth grade, and in that I was chosen for third place in the country. And then after that, in my freshman year, I competed at ISEF, which is the international fair. And for my freshman, sophomore, and junior year, I will be competing at the National Junior Science and Humanities Symposium. So I just wanted to talk a little bit about my experiences, and hopefully what I'm saying can help. Yeah, overall, just like very passionate about research, and specifically my targeted project or my targeted problem. And that's actually one of the most central things for my presentation about choosing a topic. And hopefully this presentation helps, and I'll get into that. So there's basically 5 different sections that I wanted to split this up into. I tried to give some questions just to like probe your thinking. But basically, I'm trying to split this up into 5 different steps so that you can figure out how to select an idea, focus your research. The first thing is to think about fields of interest. I think it's natural for some people to just not like physics, but really like biology, or some people to just not like any of those hard sciences, but maybe something more hands-on like an engineering field. It's a completely natural thing to have these preferences. And if you don't know them yet, that's also okay. But if you do know them, or at least if you know what you don't like, that's still information that can help you guide you through this process to pick a field of interest. After you pick a field of interest, you want to narrow down your focus and pick a problem. So I gave some ideas here. So let's say that my field of interest was environmental science. There are a lot of different environmental science problems. There's water contamination, then there's big climate change. Some people are very interested in looking at migration patterns or breeding patterns in animals. So there's a lot that you can look at in this regard. And once you pick a field of interest, there are so many problems. My advice for when you're looking at problems to focus on is that all these problems are omniscient in, or that's not the right word, but they're prominent in a lot of the different parts of our lives, and specific problems impact certain people more than they impact other people, and that's just how the world works. And I think it's particularly interesting to focus on problems that you know have a significant impact on your community or yourself, because when you can really resonate with a problem, I think you'll be able to relate to it more. You'll be more interested on working on it. And in general, you'll just be able to actually implement it, help people, and you'll have a more well-rounded aspect or approach to the problem because you understand it to a further degree. So I've been like muting myself because I still have like a lingering cough. But yeah, to go on to the third point, look at existing research. So even if you don't know exactly what you want to look at, there's so much research that's available online. So maybe look at current processes, current methods. What are scientists doing right now? And to look at what's currently there can also prompt your thinking, because seeing what's there can inspire you. It shows you what's already been done and how you can build upon it. And perhaps it'll show that there is something that you can use in a different application. So maybe someone has already engineered a certain material. Sorry, I think I was frozen for a little bit. Please let me know if you can't hear me. But maybe someone has already engineered a certain material, and you think that you can use that material for something else. And that's a novel solution, which is going to be the next point that I'll talk about. But looking at past research can really spark your thinking, because it's really hard to see a problem and then all of a sudden be like, oh yeah, there's water contamination. All of a sudden, I want to use banana peels to help that. Like, you can't just come up with that connection on your own, or maybe you can, but it's really hard to do that. And you don't have to be completely reliant on yourself to do that. There's a lot of existing research, and these are tools for you to use, and it's more than okay to use those tools. And then this goes into the fourth part about the novel solutions. So basically, after you look at existing research, you can work on your novel solutions. So maybe there are new materials, new methods, AI is becoming a big thing. Maybe there's some kind of model you can do. Just whatever this novel solution that you're thinking, it's completely okay for it to be an entirely new invention, or to build upon something that already exists, or to even just test something that exists in a new application. Whatever it is, just add your own little flair to it, do something that you're interested in, and look at this novel solution. And then the last thing is implementation. A lot of this research is very important, but I think the biggest thing is, can you actually implement it in a way to help people? Because the end goal is, can I make research that can help people? And so this may look like a variety of different things. This might be a prototype. It might be looking at different environments or settings or conditions that might be most beneficial. You might be able to develop a new model or system. And there are a lot of other applications or implementations that you can go about. So to go a little bit more in depth into fields of interest, I just wanted to give some talking points for each one, just to show like some of the key points to keep in mind. The first thing, of course, I think this goes without saying, is to pick something you're actually passionate about. If you're stuck in a field that you don't like or you don't care about, it's going to feel like a task. It's going to feel like a chore. And overall, your research won't be as rewarding as it could be if you're not actually passionate about it or interested in it. The other thing to consider is what mentors are available to guide you. Research is a really hard thing to do on your own, and mentors are a big part of this. Mentors can take a variety of different forms. It can be a teacher, it can be a peer, it can be a parent even. But think about what's available to you. And this goes into the next point about being practical. What do you have that's available? Who can help you with this? And what can you really do? For some people, they might like astronomy, but they might not have access to any of the tools. They might not have anyone to help them. And not to sound like mean and like shutting down dreams, but if it's really hard to do something, you might not be able to make a lot of progress. And maybe it is worth it to go out and try to find that help. And that might be a lengthier process, but it might be more rewarding. But just think about what's available to you and properly assess that so that you can do something practical, enjoyable, and something that you can actually, benefit from doing. So for problems to focus on, again, it's important to be practical. Think about what you actually have available. Can you actually test it? If you have a time frame or a deadline, can you actually do it within this time frame? Make sure that it's inexpensive if you can, if that's a limitation for you. If you have funding through your school or an outside program, then that's amazing. But cost for a lot of people is going to be a big point, and it is important to consider that if it's going to actually affect you. And of course, making sure that it's interesting. I talked about before, I personally think that if a problem personally has impacted you in any way, or you know that it impacts your community, I think you'll have a well-rounded perspective on it, and it might be more rewarding to focus on that. But there are definitely a lot of other interests, and that's not the only way to go about it. Again, look at existing research. It's really important to always do literature review before you try to start a novel project. There's so much research and information that's available online, so please make sure to look at that. Ask any mentors that you have about their prior knowledge, see what they have, and then also assess your own experience with the problem. Again, if this is a personal problem or something that really affects your community, there's probably a lot of information out there, even within yourself, to look for. So really think about it and see if you can gain any new perspective. For novel solutions, it's okay to not come up with something entirely new. Just look at something that shows promise. Like if you think you can truly get something out of it. I use the example of I work in water filtration, but I'm not going to suddenly say, oh yeah, a banana is going to be great for this, because I don't know if a banana can actually be great for it. And hopefully, while looking at existing research, I can actually get an idea of what I'm looking for this application. But actually look for what shows promise. You can't just pick some random thing and just hope it works. That's not how research works, and it would be very inefficient if we were to do that. So really think about what can show promise, what can be a rewarding path to go down. So one way to think about this is that if there are methods that are available, what are similar methods? What's a similar material to those that are available? And the reason to do that is that you might be able to lower the cost. You might be able to be more effective because you're choosing a better material or method to do this or carry out the solution. So that's something really important to consider. And then the next thing is implementation. So first, consider where is the problem found? What kind of setting is this and what would work there? And then of course, the end goal is to help the most amount of people, or help maybe a small group of people, but in the biggest form that you can. So really think just how can you help people? What's the cheapest way to also use the solution? Because it's great that if you have a very efficient solution, but if it's not accessible for the people who most need it, then it's not going to accomplish anything. So these are just the important things to consider. I think with AI, a lot of solutions have been able to be lowered in cost because we can transpose everything onto a virtual setting. But yeah, just think about what's going to be effective and cheap so that people can actually access your solution. And so to give a review, I'll just use an example of what I do, which is water contamination. So the first thing was fields of interest. I've always been very interested in environmental science because of its intersectionality. It's the cross between a lot of different major fields of science. It's also a lot of the social justice issues. It's very interesting to me just because it disproportionately impacts a lot of communities, and environmental science and environmental issues are present across our entire world. And I think they're very interesting and often overlooked, which leads into my problems to focus on water contamination. It's very overlooked. It's practical for me to test with the resources that I have available. And I have specifically learned about some of the disproportionate impacts of water contamination, and that particularly resonated with me, being from a city with very different socioeconomic groups present. And then I looked at current contaminant removal methods like coagulants and flocculants. I assessed that they were inefficient, environmentally harmful, or often expensive. And so after doing that existing research, it led to me wanting to design a new material. So I've been looking at a lot of different materials for While part of my most recent research was using sodium alginate because it has a high porosity, which is great for water filtration. And the reason why I went down this route was because I was able to use my existing research to assess what would be a good novel solution. And then for implementation, I thought something that would be cheap and accessible for all is a prototype of a household water filter. So that's the path that I took it down. So this is just an example of what I did. This can look a variety of different ways for everyone else, but I hope what I said was helpful. And that is the end of my presentation. So please let me know if you have any questions. And yeah, thank you. Okay, yeah, I don't think there are any questions, so I guess it'll be good to go on to the next section.
Great. Thanks. My name is Evan Gordon, and I'll be leading the next topic, which is designing and conducting an experiment. So a little background about me is that, like many other people here, I participated in Broadcom Masters in 2021. That was a great experiment. I did my project on linguistics, but no, I'm not so much interested in linguistics. And now I've been doing more, I guess, coding and web dev as of recently. And so my latest thing that I've done is I'm going to the Congressional App Challenge this spring to present about a financial education app that I made called Finance Edu. But that's enough about me. Let's get right into the presentation here. Okay, so I'm assuming that everyone can see my slides here. Since we're screen sharing, but I'll go on ahead. Hold on. There we go. Okay, so the first step is that there are 4 parts of an experiment. You got to come up with a research question, which some of our other presenters briefly touched on earlier, a hypothesis, some variables, and a procedure. Oftentimes, for traditional science fairs, I don't know about digital science fairs because that's a new thing, but historically, you put it on a poster board. Here's me with my poster board for the project that got into Broadcom Masters. That was back when I had spiky hair. Not as good as now, but that's just basically a poster board. Anyways, so we'll get into the first one, which is your research question. So that's the what. What are you researching? Your research question can be just about anything you want. A good research question is specific and is a specific topic that you're, interested in and that you want to go forwards with. I will give you an example here. It's a kind of funny example. I wouldn't actually do it for a science fair, but we'll just go with it. That is, does eating cookies make cats fat? Okay. So there it's specific. Does eating cookies and then makes cat fat? That's one thing that we can improve on, which we'll get into later in the question, because that's not specific enough. For a more serious research question, which is what I did in my presentation, I asked, will adjusting the voice onset time, which is like a linguistics property, induce categorical shifts in the perception of English consonants? Now that's specific because it refers to specific things, and you can conduct research on it. So it's really up to you what you want to do your research question on. Anyways, the next part is the hypothesis. This is actually the most important part because it'll determine how you lay out your procedure or your experiment overall. So it's the will, we say. So what do you think is going to happen if you carry out your experiment? What do you think the result is going to be? For instance, if we feed cats cookies, we would expect them to gain weight, right? So that'll be my hypothesis. Cats will experience, on average, a significant weight gain after eating cookies. Now, the actual scientific hypothesis for my project, we're going back and forth here, is that longer VOT values, that's the linguistic property I mentioned earlier, will induce a categorical shift in sound perceptions from D to T. The important thing about the hypothesis is that it's succinct or concise and clear. You don't want it to be too long or too technical. You want it to just clearly lay out what you think is going to happen. And your experiment will be trying to prove your hypothesis, although it's okay if you don't end up proving it, because you can say that. The other part of an experiment, the third part, are the variables. They're the factors. What can you adjust in your experiment? In our experiment, we have a few variables. One is the type of cookie that we're feeding our cats, the amount of cookies, like is it going to be 2 cookies a day, 5 a day, and the length of our cookie experiment. Are we going to feed it to cats for a month? How long is our experiment going to be? How long are we going to collect data for? Those are all stuff that you want to consider. Okay. The thing about variables or experiments in general is that they can fall under 2 categories. Okay, and that's my slides are out of order here, but that's quantifiable versus qualifiable. Okay, so if you have a quantifiable experiment, that's the how much. That's what you're measuring. Like if I say, will the amount of weight gains by cats increase with the amount of cookies consumed? That's a how much question, because I'm asking, or that's a yes or no question. Sorry, I have it mixed up here, but or basically I'm asking how much will the amount of weight gained by cats? That's the amount that you're looking for. How much weight will the cats gain? And then your qualifiable is a yes or no, because it's a qualitative analysis. You're looking at different qualities. So like, does eating cookies increase the weight of cats? These are 2 perfectly acceptable forms of experiments. The quantifiable ones that work with numbers, are a little bit more common, but whatever you choose, you just need to make sure it goes with your hypothesis. Okay, so the specifics here, we can begin with quantifiable ones, right? That's the numbers. I have to go back a bit, but there we go. So quantifiable, you would use a system of independent versus dependent variables. So for independent variables, that's the variable that causes a change. What causes the change is what we're looking at. And dependent variables are what represents the change. In other words, the dependent variable is dependent on adjusting the independent variable. So in our cat experiment, what happens is we adjust the amount of cookies, right? And that causes a weight gain to change. So the weight gain is dependent on our independent variable, which is the amount of cookies. The amount of cookies affects our weight gain. So there's your relationship. The variable that you control is the independent variable, and the variable that's dependent on what your independent variable is, or dependent on what you control, is the dependent variable. You're measuring that in your data collection. Okay, so the other category is qualifiable variables, right? For qualifiable experiments, that's the whether or not it does or doesn't, yes or no sort of thing, or different categories. You have something called the control versus experimental group. And the control group is you separate your study participants into 2 groups. Let's say in our cat experiment, we have to test whether or not cats gain weight if they eat cookies. We put them into 2 groups: cats who eat cookies and cats who don't eat cookies. So our control group is the group that we're not applying the treatment or change to. So our control group here would be cats who don't eat cookies, because we're not feeding them cookies, so without the change. Our experimental group is cats or whatever the subject is that you apply the change to. For instance, cats who are fed cookies. So our hypothesis was, does eating cookies make cats fat, right? So to do that, we need to measure weight gain, but since it's a yes or no question, that's the key word, means yes or no, we need to separate it into control or experimental groups. The yes or the does is the cats who are fed, and then the control, which is just if you don't make any change, is cats who are not fed cookies. Okay, here's another important part, which is the procedure. Okay, because you can design an experiment, but then you actually need to conduct it. Now, what science fair judges want to see in your procedures are something that's detailed. Okay, so in order to make it detailed, you need to follow you need to have a few different things. It needs to be specific, you need to have controls, and you need to produce measurable results. Let's start with the specific part, okay? So, and this goes along with the controls. There are plenty of things that can throw off an experiment. Let's say you're testing whether or not cat eating cookies leads to cats gaining weight, right? Like we are. There are a bunch of different factors at play, right? Like you could have a cookie for different types of cookies, for instance. Like, what if I feed this cat a chocolate chip cookie, another one oatmeal raisin? What if I feed one cat 10 cookies and the other cat 5 cookies? Now, to make sure that the results are consistent or they actually make sense, you need to have controls. Those are factors that stay the same no matter what subject it is, okay? So, for instance, in our case, the controls, if we wanted to design an experiment about cats and cookies again, we would say something like, each cat will have 5 cookies for one day each week, for each day for 1 week. So it's very specific, right? And it's the same for each group. We know that each cat is getting 5 cookies and they're going to have it for 1 week each day. So that's good because it fulfills the requirement of being specific. So we don't have to worry about there being inconsistencies or like, because if I didn't specify that, and I fed all my cats different amounts of cookies, then it wouldn't be very consistent, right? Like, how would you actually know that what you're measuring is what causes a difference? How do you know it's not something else? So the other part is when you conduct an experiment, you want it to prove your hypothesis, right? So that'll be the next topic, but you need to produce measurable results. So in order to do that, for instance, you got to make some recordings done and make sure that you specify that in your procedure. Because the way that people get points on their procedure is just being specific, outlining clearly what they're going to do. Here, for instance, we need to record the weight of cats before with each scale. Let's like even specify the model or brand of a scale. The more specific, the better. Then after that, you need to record the weight of cats after with the scale. Now, notice how I didn't write analyze data, because analyzing data is a separate thing. Don't write that you're going to analyze data or how you analyze data. That's under discussion or results. So it's just the actual part about conducting an experiment is your procedure and collecting data. So what you keep is what you need to record your data. That's what goes in the procedure. And what you don't put in your procedure is how you analyze the results. That is separate. In my case, for my linguistics experiment, I was having people listen to sounds and tell me like what word it sounded like. Like, did it sound like bat or tab or tat or bat? In that case, I wrote down a procedure like the volume level of the microphones, like 60 decibels. And I provided a bunch of details, like how many times does a participant get to listen to the sound? And basically, I just tried to add as many details as possible. But the main thing is you put in stuff, for procedure, you put in the things that you need to record data, and you leave out your data analysis. Now, those are the main steps for designing an experiment. And I think that I'll stop sharing now. But if anyone has any questions about how, for their project or how they could apply that, I'm happy to take that.
Yeah, we had 2 questions. So basically, the first one was, what questions do judges typically ask at science fair, and how should we prepare for the questions?
Well, it depends on what level of the science fair are and the judge. At local fairs, they're going to be a lot more interested maybe in your inspiration, like what what factors, like what led you to do this experiment? Like if you're talking about an experiment, like, okay, what type of soil prevents flooding? Like say you might it might be because like, oh, our house has gotten flooded a lot, our community experiences flooding, and I wanted to solve that. So your local fairs might ask more about, from my experience, what inspired you for a project. And then the state fairs, state or even Broadcom, the national fairs, it'll get a little bit more nitty-gritty into the methodology. In my case, you had state fairs. I asked one thing that they did ask me for is a lot of clarifications about my procedure. They would ask, like, for instance, I had one judge I remember who asked me, um, like, um, in what were participants able to change their answer after listening to it the first time? And I had to tell them, no, they weren't. But basically, if they'll have oftentimes a lot of questions about your procedure, or maybe even how you analyze data that local fairs weren't. So just remember that you need two things. The questions fall into two categories. One is, what is your inspiration? Why are you passionate about it? And then the other part is what I call the hard ones that are actually about your experiment, your project. Oh, and a third category is I forgot to mention it, but it kind of goes under the inspiration is a lot what we talked about in the previous section was your inspiration, or sorry, I meant the applications of your experiment. Like if you're talking about, let's say, maybe about the flooding or different types of soils that are used to mitigate flooding, like what are your applications for it? Like, okay, by knowing that I use this soil, I can make sure that gardens around my community or around the nation don't flood or plants don't flood. So that was a little bit long, but those are, I guess, the main types of questions that I have asked. Just remember, it'll get tougher the higher level you go up anyways. So I guess the next question was, what if the hypothesis was found to be wrong after your research? Well, what I say is that if your hypothesis was found to be wrong, it's not that much of a deal for local fairs. Um, so in my case, I actually saw a rubric for the local fair that talked about whether if their hypothesis was wrong, you could still get credit if you had your procedure, your analysis, your experiment. So the main thing is that if you're in a local fairs, you don't have to worry about as much as long as your project looks put together. But if you want to get to the next level, the state fair, I would perhaps try a different project, or you can always adjust your hypothesis too, right? Like, let's say I said something like on our cat example, something absurd happened. Like, it'd be crazy, right? If cats actually lost weight from eating cookies. But if that's what you found in your experiment, you could change your hypothesis to, will cats lose weight by eating cookies? But yeah, it's kind of up to you on how you approach that. But that would just be my advice.
Okay. I also want to add to Emin's question, well, Emin's answer for the first question. Some common questions that I encountered were like, what was the hardest part of the experiment? And also, like, what did you find the most interesting, and like next steps or what you could improve on your project? If you want some like, well, the second part of the question is how should we prepare for the questions? You can, um, present to like parents, teachers, friends, and if these people have any questions, you can answer them in terms that they understand, and so you can practice answering them and making sure that other people understand. And so, how you should prepare is just find people who don't know your project, don't know it very well, and present. And also find people who do know it well, because in cases of professionals at science fairs, they do know this field, and so you should also be prepared for specific questions. And so just in general, just make sure that you find a lot of people to present to, you know your project well, and that you're able to answer these questions.
All right, then I'm gonna go next. So, can you guys see?
No, I can't see. It's just like a black screen.
That's weird. Let's try again. Hold on. Can you see now?
Yeah.
Okay, cool. All right. Hi, everyone. Thank you so much for being here today, and I truly appreciate your guys' time and presence. I'm Ivana Haval, one of the co-founders of YouthSTEM. I was a Broadcom Masters Top 30 finalist in 2020, an ASU National Sustainability Solutions Fair first place winner in 2021, a Robin Melanie Foundation Sustainability Award winner, national level competition, and I won first place there, NC Student Academy of Sciences second place winner 2024, NC American Water Works Association first place in 2024, and NC Water Environmental Association first place in 2024. I've been passionate about STEM research since probably the 6th grade, and I've worked towards gaining research experience under the mentorship of various professors in nanomedicine. So nanomedicine combined with in-depth understanding of cancer cell metabolism for non-invasive medical drug delivery applications is my major area of interest. So welcome to my presentation, Data Collection Analysis, Unveiling Insights. So today we'll explore the importance of collecting and analyzing data along with some key methods and tools used in this process. So what is data? Data refers to the raw facts, figures, observations, measurements, or information collected or generated during the research process. It can be in the form of numerical values, texts, images, audio recordings, or video footage, depending on the nature of the research and the methods used for data collection. But how exactly do you classify data? Data refers to information, facts, or statistics collected for analysis or reference. It is essentially raw material that can be processed, interpreted, and analyzed to extract meaningful information and understanding. Data can be classified into various types based on different criteria, such as quantitative data and qualitative data. Some subtypes of this data include time series data, which is collected over successive or evenly spaced time intervals. Text data includes written or typed words, sentences, or paragraphs, and even multimedia data, which includes a combination of audio, video, and image files. So what is quantitative data? Quantitative data consists of numbers and measurements. It is used for finding patterns or relationships between things. We collect quantitative data by counting or measuring things. This data here is gathered through surveys, experiments, or by looking at numbers in existing records. In our example over here, the advertiser asks 200 customers to report precisely how many days per week do they read a daily newspaper. And as you can see, 44 people report they've never read a newspaper. 22 people report that they read the newspaper 5 days a week, and 30 people report that they read the newspaper all 7 days. And as you can see here, how a table can be created and how the data is presented in a clear and structured form. So now what is qualitative data? Qualitative data is information that does not consist of numbers or measurements. Instead, It describes qualities or characteristics. It's usually about descriptions like words or pictures, and it helps understand things like people's thoughts, feelings, or actions. We collect qualitative data by interviewing people, observing them, or looking at the things they create. So at what stage is data collected in the research process? Data is collected after you identify your area of interest or the problem you want to solve. You review your literature or sources. You then formulate a research question or the research objective, designing a methodology, and last but not least, you gather your data using the chosen methodology. So basically a summary of what everyone else is talking about so far. So let's look into the available tools we have for data collection. In scientific research, various tools are employed to collect data depending on the nature of the study and the specific field of science, like observational tools such as telescopes, microscopes, or sensors to observe and record phenomena, laboratory equipment such as spectrophotometers, centrifuges, chromatographs, and specialized instruments to collect specimens, conduct experiments, and analyze samples. Field instruments such as GPS devices, data loggers, weather stations, and soil samplers for collecting data in outdoor and remote environments. Computer software and applications to use for data entry, analysis, and visualization. Surveys and questionnaires to gather information from a large number of participants. And last but not least, interviews conducted to obtain detailed qualitative data. So the most common ways the data is represented could be in the form of tabular data, as charts where data is arranged in rows and columns, graphical representations like pie charts, as you can see here, bar graphs, line graphs, area graphs, pictographs, box and whisker plots, and diagrams to visually display trends, relationships, or comparisons in the data. Textual data such as documents, reports, and files, mathematical models such as algorithms and mathematical representations used for analysis and prediction, geospatial data that represent maps and spatial information, temporal data that represents changes over time, mostly changes in weather patterns, monitors traffic conditions, studies demographic trends, and more, and networking data, which provides information about how different things are connected and related to each other within a network. All these representations can be used individually or combined to best convey the information to support the interpretation and communication of findings. So what constitutes data analysis? Data analysis and research means turning this raw data that you collected into useful information that helps researchers to draw important conclusions by testing their hypotheses, identifying patterns, making important observations, deriving meaningful insights, drawing comparisons, detecting outliers, summarizing findings, advancing the knowledge, and ultimately solving problems. It is a crucial step in the research process that transforms raw data into meaningful information. So, what is the purpose of data collection and analysis? Data collection and analysis are pivotal in research for evidence-based decision-making, validating findings, identifying trends, hypothesis testing, problem-solving, predictive modeling, optimization, improvement, and decision support. They enable research to draw informed conclusions, address challenges, and anticipate future scenarios, optimize processes, and support decision-making across various domains and fields, ultimately advancing collective knowledge. So, how do you go about conducting data analysis? So you begin analyzing data by looking at your data by comparing groups, finding averages, or seeing if findings are related or have a correlation. Then you interpret your results. Think about what your data means for your project and draw conclusions. Share your findings. Next, you want to communicate your findings with peers, teachers, and mentors, and compile what you find into a report, presentation, or a poster. You then want to get feedback, so ask whoever you shared your findings with what they think about your project and then use their ideas to make your project even more informative and better. Next, you want to reflect. So think about what you learned and how you can do better next time or improve upon your project. And then last but not least, you want to celebrate. So be proud of what you accomplished and what you learned from analyzing data for your project. So thank you so much for your time and attention today. I appreciate the opportunity to present to such a respectful and amazing audience. And remember, today's data empowers tomorrow's possibilities. Thank you.
All right. Hello, everybody. My name is Sohan Govindaraju, and today's topic is going to be about how to create a poster. So here are a couple examples of various posters that we have here. Here's an example of one for the Intel ISEF Science Fair, which I know people have been talking about. Here's another one from the fellow Intel ISEF Science Fair competition. So the key elements of the poster that we're going to be talking about here is obviously the title, the research question, as Rika explained, how you have to be able to communicate. But the key components that I want to specifically focus on is your data analysis, background info, and conclusions, all of which you need to be able to convey through the poster. And the poster is supposed to be like a supplemental aid to whatever you communicate when you're talking to the judges, or when you're talking to parents or fellow volunteers, etc. Okay, so just a little bit talking about just saying some context from middle school poster regulations. Typical size is a 36-inch by 48-inch size poster board, so a normal size, relatively normal size poster board. And this is what's typically done in middle school. High school is a little bit different. They have a bigger size poster just because there's more information that high schoolers are publishing compared to the middle schoolers. However, middle school, there's no set regulation. Okay. So here's an example of a poster board that I had. This was from sixth grade for me. Um, as mentioned earlier, a lot of my fellow Broadcom masters or ISEF finalists, a lot of us are focusing on environmental. That's one of the themes that I observed today, and I focused on water leaks. Lately, I've been focusing over the past 5 years, been focusing on wildfires, specifically understanding the spread of the wildfires, modeling in terms of that, and evacuation strategies. But in sixth grade, when I made this poster, this, as you can see, this is a normal size poster in the sense that it's a 36-inch by 48-inch size poster board in which I had this abstract, background research, prototype, testing procedures, everything that was mentioned beforehand on how the good components are for a science fair project, along with data schematics, graphs, and conclusions and next steps. So the one thing that I want you to kind of observe here is the use of pictures, which I'm going to be going more in depth a little bit later. But schematics for engineering design projects, which we're going to talk about, are very important, along with data tables that clearly identify the data and what you specifically want to highlight to the judges so that you can refer to. The biggest thing about the poster board, in my opinion, is that you need to be able to use it to help with the flow of communication, as Rika explained. It's supposed to be serving as an aid. You're supposed to use the poster board and refer to it. That way, the judges will be able to know that you know what you're talking about and you made this poster board and that you can use it for your explanations. So the poster board can be used for your benefit. So use it. Okay. For high school poster regulations, as I said, it's a little bit bigger. Front to back, 30-inch or 76 centimeters, 48 inches or 122 centimeters for width. For height, 108 inches or 274 centimeters as defined by the ISEF display regulations. Much bigger size poster board. Okay. So what we need to talk about here is for the science inquiry versus engineering design. There's a little bit of set differences when it comes to making the poster. So as explained in the last slide by Vivana, the scientific method is kind of where you have to ask a question, make a hypothesis, do background research, and kind of look into seeing whether your experiment is working or not, procedure working. Whereas the engineering design method, the key difference is that you're building and innovating something, whether it be a box fan, whether it be a cool new iPhone product or something. The engineering method is involving demonstrating and building something that's tangible and can be shown via pictures or whatever else. Okay. So this slide here kind of details the key components that you need to have in a science inquiry-based project, what you should have in your poster board. So as always, try to have a title page with your student name, your name, project question, and your hypothesis, along with what hypothesis you propose to answer to your question. So you should have like a research background question, and the hypothesis should answer that using key fundamental terms. I believe there'll be a workshop on that later, which kind of explains hypothesis development, along with procedures. How did you design your experiment? Kind of detailing all that in your post board. The key thing for me is really this results data tables graphs. Oftentimes I see them being very, very small in various poster boards, especially in the middle school level. I think this needs to be very big because that's really the heart of your project. If you have small data tables and graphs, then the judges won't be able to really see what the goal, or what were the results, and what were the goal, did you achieve your goal or not with this project, kind of answering, tying back to the hypothesis. Finally, conclusions and analysis. That's another big takeaway, because you got to be able to say to the judge or whoever else with the poster board that either my project really matched my goal or met my hypothesis, or it didn't, both of which are fine, but you got to clearly and explicitly mention that, and really how does your data apply and analyzing that. Okay. Last point is really the bibliography, really where your sources are and applying those, because when you do background research and everything, when you're trying to do research about your topic initially, you're going to get information about that. So making sure you source that, and maybe have a little uh, portion of your poster dedicated to that, or maybe even a separate reference sheet altogether for the bibliography is important. Okay. For the next slide here, which is about engineering design, as I explained 2 slides ago, this really only applies if you're kind of designing and developing a design, but it has similar components as a science inquiry. For example, the student, you make sure you have your name, the title, what problem you're trying to solve. Notice the key difference here is that you're not mentioning a hypothesis in the engineering design projects, but you have this design and methods, and as Eamon mentioned, you have the procedure and construction and testing protocol, kind of defining the scope of your engineering design project. Once again, the results, making sure that you reference graphs, tables, etc., making sure you enlarge them. That's important takeaway from this slide, along with bibliography, and additionally, what is analysis. These components should all be mentioned in your poster, just so that people can refer to them and see what it is, what your project is, without you giving a speech. It should be able to serve as an aid, as what I've been trying to reiterate here. Okay, next slide, talking about graphs, table, and conclusions. Again, I just want to make sure I hit the point home that the graphs and tables should be visible and noticeable. They cannot be really tiny. You got to make sure that you can see them from the distance, because these are the key components and really the heart of your project, in the sense that if you're able to have these, then it would show that what the impact of your project is. Okay? So the key lessons that I want you to understand from making a poster board is, when it comes to data, making sure that it's big, it's large, and it's able to clearly reflect what you're trying to communicate. Use image and less words. As the great scientist Albert Einstein once said, one picture is worth 1,000 words. So when it comes to background info and stuff in which you don't need to have a full paragraph, maybe think about using images instead. I think images are a great way to communicate the situation. For example, for me, wildfires, one of the images that I have on my poster board is an entire map of the United States, showing regions in which there is a high intensity or a high likelihood that a region is going to be susceptible to a wildfire. So this will be able to show that, for example, in the Western United States, where I live in Oregon specifically, we are at high risk for a wildfire in Oregon and California. And the last point for the critical lessons for a poster board is, you want to convey critical items. So whatever you think is important, make sure that you clearly and specifically, whether it be bolded, enlarging it, whatever you need to do, make sure that it's clearly noticeable in the poster board. So how to make a poster? There's really three different options that I generally use. There may be more, such as physically hand drawing or whatever you need to. But if you want to make a professional poster board, one of the best options that I've learned recently is Canva. Canva is a great tool for making just posters in general, and you can clearly be able to label, and it pretty much serves as the same function of slides, which I've generally used before, slides in PowerPoint. But these three are excellent options that you can use to really create and make your poster to make sure that you're able to create small items, for example, captions, or you want to enlarge your graphs and everything. It's a really great way. I would highly recommend using any of these three options, in fact, to create a poster. Thank you for listening. Please let me know if there's any questions in the chat or audio, whatever works. Thank you. So I see here, how do we balance text and pictures in the poster board? That's an excellent question. I think for me, at least the way I like to do things is for the background info, I like to rely less on heavy words and I like to use pictures. It depends on person to person, if I'm being honest. But the reason why I like to do I like to put pictures for the background is because I can, for the judges, they react more. What I've noticed is that they react more to seeing a picture in which you have different color schemes and everything. And the general rule of thumb is that if you have a picture, make sure that you have a caption or something which kind of explains it. But for stuff that requires like text, such as hypothesis and stuff, and procedure, you really have no choice but to use text and type whatever you're trying to convey. But being able to use some pictures in background, making sure you use it obviously in your graphs and tables, excuse me, and schematics. Those are all ways that you can utilize pictures instead of text. Great. I don't see any more questions in the chat, but as always, if you have any more questions, just put it in the chat or verbally, whatever works. But thank you for listening.
Okay, this concludes our meeting for today. Thank you for coming to our science fair workshop. If you have any more questions, you can always send them to youthstem21@gmail.com. If you don't remember what the Gmail is, you can always go to our website and contact us. And also our Instagram, I'll send in the chat our website and Instagram. And always, if you have any questions about science fair research or need any advice, again, you can contact us and we'll have somebody here that has a lot of experience in, Broadcom Masters, ISEF, whatever, to help you. And so if there are no more questions, I'll end this meeting for today. And again, thank you all for coming.
Thank you for listening.
Take care.